Bismillah ar-Rahman ar-Rahim. Today we will talk about a very important type of series called alternating series. So what is an alternating series and how to test them for convergence? That's our main task today. So what's the meaning of alternating series? Alternating series is a series whose terms are alternately positive and negative. Meaning, when you take the readings, the first reading, for example, became positive, the second one is negative, the third one is positive, then negative, positive, negative, and etc. So this is called alternating series. We formulate it in mathematical like this. N equal to 1 up to infinity, minus 1 to the n minus 1, bn. We need these bn's to be positive, all the time greater than 0. So in this case, if you substitute n equal to 1, you have b1. Because this will be minus 1 to the power 0, which is 1 times b1. The second term, you substitute n equal to 2, you have minus b2. Then the next one will be plus b3, then minus b4, then plus b5, and etc. Once we assume bn is positive, we are sure that we have positive here, then negative, then positive, then negative. This is called an alternating series. The question is, how to test this series for convergence? We have a very nice test called alternating series test. Okay. The test says if you need to check for convergence of this series, first you need to have the alternating series, then you can apply the test here. It says if the alternating series, which is given by this standard form, let us say, satisfies these two conditions. The first one, bn plus 1 less than or equal to bn, meaning the readings bn is a decreasing sequence. And the limit of bn as n goes to infinity is equal to 0. If this condition is satisfied as well as the second condition, then this test says then the series is convergent. We call it convergent by alternating series test. Okay. We need to be careful here. We have one statement which is one direction only. If the alternating series satisfying the first condition, the second condition, the result, then the series is convergent. It is not if and only if. If this is satisfied, then the series is convergent. Okay, how to apply this test in examples? Let us take the following exercise. The exercise here, exercise number 1 says, okay, it says test the given series, the series which is given by the following here. This is very famous one, n equal to 1 up to infinity. We need this example later when we talk about absolute and conditional convergence. This is minus 1 to the n minus 1 over n. Test this one for convergence. Of course, by looking for the shape of the series, we should know that this is an alternating series. And since it is an alternating series, we can apply the alternating series test. Now, the only thing we need to check is the first condition and the second condition. So, rewriting this in the standard form, it is already in a standard form. So we need to deduce what is bn here. Bn is equal to 1 over n. Because this is what? This is the summation. N equal to 1 up to infinity. It is minus 1 to the n minus 1. Bn, that is 1 over n. So our bn here is 1 over n. It is an alternating series and bn is equal to 1 over n. We need to check these two conditions now. Is this sequence of bn decreasing? Meaning, is bn plus 1 less than or equal to bn for all n? Is it true for all n? Let's check this. We know that n plus 1 is greater than n for sure. This is true for all n greater than or equal to 1. This is always true. The reciprocal now, 1 over n plus 1, 1 over n plus 1 must be less than 1 over n, and this is for all n greater than or equal to 1 also. Now what is 1 over n plus 1? This implies we have bn plus 1 is less than what? Less than Pn. This is true for all n greater than or equal to 1. So we have the first condition that Pn plus 1 is less than or equal to Pn. Okay, fine. That's the first condition we have. So the first condition here is satisfied. The second condition. What is the limit? We need to check this. What is the limit as n goes to infinity of the Bn? That's equal to the limit as n goes to infinity of 1 over n. And clearly this is equal to what? This is equal to 0. So coming back to the discussion now, we have the first condition of the alternating series test is there. We have the second condition of the alternating series, that is the limit of bn equal to 0. What is the conclusion now? This series is convergent by alternating series test. This series is convergent by the alternating series test. So, by, let's say, alternating series, test what? The series, the alternating series given as the series is convergent. Okay, so this is direct application for this alternating series test. So the only thing we need to check are two conditions, the first one, second one. If it is an alternating series satisfying these two conditions, the answer will be gained directly by this test, and this test says the series is convergent. Okay, we'll see more examples. Maybe if one of these conditions will not be hold true, what will happen, and etc. Let us take another example. Example number 2 says, do the same, test this series, which is given by this, which is summation of, we have n equal to 1 up to infinity, that is minus 1 to the power n minus 1 multiplied by n squared all over, that is n cubed plus 1. That's the series we have. Test this series for convergence. Test this series for convergence. Okay, we have to deduce what is, first of all, we need to observe this is an alternating series. It is an alternating series. This series is alternating series. This is an alternating series. So we can apply this test with the following. It is an alternating series with Bn is equal to, defined by n squared over n cubed plus 1. Okay? N squared over n cubed plus 1. That is the formula for Pn. We need to check two things. First, is this sequence is decreasing? The sequence of Pn, is Pn plus 1 less than or equal to Pn for all n? That's one thing. And the second one, is the limit of this as n goes to infinity, is the limit of Bn as n goes to infinity equal to 0? Okay, we need to check these two conditions. I will start with the second one. That is so simple. Clearly we have, what is the limit as n goes to infinity of the Bn, which is n squared over n cubed plus 1. Okay, we have the degree of the numerator is less than the degree of the denominator, and these are two polynomials, so for sure this will go to 0. To show this, you just divide by the n cubed. So this is n goes to infinity. Here, if you divide by n cubed, this will be 1 plus 1 over n cubed. Okay, and if you divide by n cubed upstairs, that will give you 1 over n. And we know that 1 over n goes to 0. This goes to 0 as n goes to infinity. This goes to 0. So what they have is 0 over 1 plus 0. That's equal to 0 over 1. That's equal to 0. So yes, the limit of Bn as n goes to infinity equal to 0. It remains now to show that this sequence is decreasing. How to show that this sequence is decreasing? If you remember when we discussed sequences or decreasing sequences, we studied some strategies to deduce that a sequence is decreasing or increasing. And one way to do it here, we can define a function that agrees with the sequence at the integer point, okay, the positive integer points, and then show that that function is decreasing using calculus, which is the derivative. So that's exactly what we will do here. So I will define a function here. Let f of x to be equal to, I get the same expression here, x squared over, let us say, x cubed plus 1. That's exactly what we have. Note that here f of n is nothing but Bn. This is what we have. Okay? Let's try to show that this is decreasing by using derivative. So I will find the derivative of the function f prime of x. Derivative of this is 2x multiplied by x cubed plus 1 minus, the first one is x squared, derivative of the second one, that 3x squared. Okay? And then this is all over x cubed plus 1 all squared. Fine. So this is equal to, if you simplify, this will be 2x to the power 4 plus 2x minus 3x to the power 4. Okay? All over, this is x cubed plus 1 all squared. Now simplifying more, you have 2x to the power 4 minus 3x to the power 4. So that will be minus x to the 4. So we have 2x minus x to the power 4 all over x cubed plus 1 all squared. Fine. This is equal to, now if we take x common factor, so we have x times 2 minus x cubed all over x cubed plus 1, okay, all squared. This is what we have. Now we need to check one, this is positive, one, this is negative. Clearly, if you just look carefully for, okay, this is infinity, and this is what we have here. Let us say this is 0, and we need to find the zeros of this, okay, which is cubic root of 2, cubic root of 2. If you check the sign diagram of this expression here, yani if you take a point after this, let us say, for example, 3 or 4, this will give you positive, this will give you negative, so the multiplication will give you negative. This is always positive. I don't care about what's happening before actually, but if you like, we can take a point here, a point there, we don't care. The only thing we know that this function here, this is what we care about. After this number, cubic root of 2, this is a decreasing sequence. So we can show now, we have shown that this sequence is decreasing for all n greater than what? Cubic root of 2. So let us start from n equal to 2. This is always decreasing. So we know that now Pn plus 1, Pn is decreasing for all n greater than or equal to 2. So from n equal to 2 and so on, this is always decreasing. Fine. So Bn plus 1 is less than Pn. Okay? That's what we need to show. So it is decreasing for all n greater than or equal to 2. So it is not affecting convergence here. We can just replace n by 1. So this is n equal to 1. This will give us 0. This will be 1 over 1 plus 1, which is 2. So that is one single term. And then we start from n equal to 2 up to infinity. So if we can show that from n equal to 2 up to infinity, the series is convergent. Convergent means it has a finite sum. Adding a finite sum to an element, which is also finite, of course, the answer will be finite. So it is not a big deal if you can prove that this is decreasing starting from a certain integer, finite integer, up to infinity. Still, you can use what we call alternating series test. What is the conclusion now? We have a decreasing sequence, and its limit as n goes to infinity equal to 0. We have an alternating series. So the answer is, by alternating series test, the series is convergent. So the series is convergent by the alternating series test. Okay? So it is convergent by alternating series. This is how to apply alternating series. We will see more examples, at least one example where one of the conditions is not holding true. Okay? So this is part B, let's call it, or another exercise if you like, says do the same, test the series given by this, minus, this is n equal to 1 up to infinity, this is minus 1 to the power n plus 1, okay, and that is 3n all over 4n minus 1. Minus 1 to the n plus 1, minus 1 to the n, minus 1 to the n minus 1. It doesn't affect anything in the alternating series. Minus 1 to the n plus 1, you can rewrite it as minus 1 to the power n minus 1, the same. Okay? So this is not affecting the type of series we have. Test the series for convergence, of course, for convergence. Okay? This is what we have. So again, we can observe that this is an alternating series. I prefer always to start with the second condition. This is myself, okay? I start with the second condition. If it is there, then I move to the first condition and show it is decreasing. Now, what do we have for Bn? Bn here is equal to 3n divided by 4n minus 1, okay? 4n minus 1. We need to be careful here. We need to be careful here. Okay, this is an alternating series. Fine. What is the limit of this as n goes to infinity? What is the limit of Bn as n goes to infinity? We have Bn is 3n over 4n minus 1. So what is the limit? This implies the limit as n goes to infinity of Bn, which is exactly equal to the limit as n goes to infinity of what is Bn? That is 3n divided by 4n minus 1. Clearly this is equal. If you divide by n in the numerator and denominator, this is what you have. N goes to infinity. This is what we get. 3 over, this is 4 minus 1 over n. And clearly as n goes to infinity, this goes to 0. So the answer is 3 over 4. Fine. Now, it seems that the second condition of the alternating series is not there. The limit of Bn, so we check the second condition in the theorem or the series test, the alternating series, it is not equal to 0. What is the conclusion? If this is not equal to 0 and it is an alternating series, then for sure the series is divergent. The series is divergent. But why? Why this is divergent? Let us look at it again. Is it divergent by alternating series or it is divergent by another test? Okay. Consider the whole thing here as an, we called it before. Okay. The question is, why the series is divergent? So the conclusion, if this is not equal to 0, this is not equal to 0, okay? So the series is divergent. But the question is, why it is divergent? Is it because of the alternating series test? The answer is no. Look carefully for the series again. Now, what is the limit as n goes to infinity of an, the nth term of the series? As n goes to infinity, I mean by that minus 1 to the n plus 1 or whatever, 3n all over what? 4n minus 1. You know from before that the limit of this does not exist, because if the limit of this one does not go to 0 and this is alternating, so the limit does not exist. So the limit is not equal to 0. Actually does not exist or not equal to 0. The limit is not equal to 0 or does not exist. We have a very nice test before, says, if the limit of the nth term is not equal to 0 or does not exist, the series is divergent. So why this is divergent? It is divergent. This is the reason here. Why it is divergent? It is divergent by what we call the divergence test. What is the divergence test? I will remind you of this. The divergence test says, if you have a series n equal to 1 up to infinity, and you have a series where we have the nth term is given by an, the test says, if the limit as n goes to infinity of an is not equal to 0, or the limit as n goes to infinity of an does not exist. What is the conclusion? This implies the series is divergent. The series is what? Divergent. Okay, so that is what we call nth term test of divergence, or simply divergence test. So we use here divergence test to conclude that the series is divergent. This is what we call alternating series and alternating series test. The second point we have is talking about again and again, if we have a convergent series, we need to estimate the sum. So what is the error involved in estimating the sum for alternating series? That will be our next point. Now, after we discuss the convergence of alternating series, we need to know how to estimate the sum if the series is convergent. This is a nice theorem talking about estimating sums. It says if you have a series of alternating type, so we have n equal to 1 infinity minus 1 to the n minus 1 bn, so this is the standard form we need to write the series on, is the sum of an alternating series such that we need the sequence here is decreasing, bn plus 1 less than equal to bn greater than equal to 0, and we need the limit of bn equal to 0. The meaning of these two conditions that our series is convergent. Because if we need to talk about the sum, the series must be what? Convergent. So these two conditions will just tell us that this series is convergent. Fine. If it is convergent, then this theorem says the absolute value of the error Rn. What is the meaning of Rn here? If you need to take an estimate of the sum, always you take a partial sum. So if you take the first n elements as it's your partial sum, Sn, the remaining terms will be called Rn. So this theorem says Rn, which is the difference between the total sum and your partial sum of estimation, is less than or equal to the preceding element Pn plus 1. So that is very nice theorem, very strong theorem, tell us something about an upper bound for the error, absolute value of the error, always bounded by Bn plus 1. So what is Bn plus 1? It is the next element in the sequence. So let me just say something here. This is the sum we have. The sum is, we said B1 minus B2 plus B3 minus plus etc. up to, let us say, Bn minus Bn plus 1 plus etc. If we need to estimate the sum, always this S is approximately equal to Sn. So this theorem says, if you stop here, and this will be called Sn, so S is approximately equal to Sn, you have an error here. This is called Rn. This theorem says absolute value of Rn, which is the difference between S and Sn, taking this one to the other side, is less than or equal to the value of the next element in the sequence Bn. So it is Bn plus 1. That's exactly the statement of the theorem, keeping in mind that we have an alternating series, and that series is convergent. So before we use the theorem, we need to prove the series is convergent, and then we can use the theorem to estimate the error involved in estimating the sum. So let us do that for these two exercises. These are the two classical, concerned about alternating series. Either we shoot for a certain accuracy, or we need to know how many terms we need to add so that we have a certain accuracy. These are the two exercises. The first one of them says, find the sum of the series, which is given by this, correct to 3 decimal places, meaning our error, we need it to be less than 0.001. Okay? So we need, this is another way to say this, we need the error here to be less than 0.001. So that's correct to 3 decimal places. So what should we do now? If you open the sum is equal to what? If you just substitute 0, that will give you what? Okay, first of all, do you have n equal to 0 or we have n equal to 1? We need to be careful about this. We have here in the exercise that is starting from n equal to 0 up to infinity. So before I go and use whatever I have here, let me just put it in the form of the series we have here. So what do we have is, this is summation from n equal to 0 up to infinity. So I need it to start from 1 up to infinity. So that's exactly what I need to put it. N equal to 1 up to infinity minus 1 to the n minus 1 times Bn. So I shift the index by 1. I increase by 1 here. N equal to 1. So what I need to do inside to decrease by 1. So that will be what? Minus 1 to the power n minus 1 divided by, this will be n minus 1 factorial. Okay? So in order to use the theorem, I need to have it in a standard form first. Okay, fine. Now, n equal to 1 up to infinity, if you just open this, open a few terms, what do we have? If, first of all, is it convergent or not convergent before opening and etc. We need to know, is it convergent or not convergent? He said find the sum correct to 3 decimal places. We need to use the theorem here, so I need to check if this is convergent or not convergent. Okay, let us check if it is convergent or not convergent. Then we just open a few terms. Let us discuss convergence here. Now 1 over n minus 1, Bn is equal to 1 over n minus 1 factorial. So this is, Bn plus 1 will be what? Bn plus 1 will be 1 over n factorial. Clearly now we have Bn plus 1 is what? Less than or equal to Bn. This is we have. Why? Because you know n factorial is larger than n minus 1 factorial. So 1 over n minus 1 factorial will be greater than 1 over n. So this is holding true. This is one thing. The second condition, if you like, the second condition, this is one condition here we have. This is the first condition. For the second condition, clearly we have this also. The second condition says what is the limit? What is the limit as n goes to infinity of 1 over n minus 1 factorial. What is n minus 1 over n minus 1 factorial? It is 1 over 1 times 2 times 3 times 4 times n minus 1. You can easily show this is equal to 0. Why? Because 1 over n minus 1 factorial, this is greater than or equal to 0 and less than or equal to 1 over n minus 1, if you like. And as n goes to infinity, this goes to 0, this goes to 0, so the middle one also going to 0. So yes, the series is convergent, everything is fine. We are satisfying the first and the second condition. Now we need to know only how to estimate the sum so that the sum will be correct to 3 decimal places. Simply what you need to do is the following. You find the sum equal to, just open a few terms. If you substitute n equal to 1, this will be 0 factorial, which is 1, and this will be 1, so we have 1. I will just copy some numbers here because we need a calculator. This is minus 1 over 1 factorial, okay, then plus 1 over 2 factorial, and you move like this, you reach up to what? You have here plus 1 over 6 factorial and etc. Then you have minus 1 over 7 factorial plus something like this, okay. Now, let me just erase this one, I don't need it. And let us see why we reach up to 1 over 7 factorial. This is s equal to this. Of course, this will continue. I need to know where to stop. And then I need to add my sum. So where to stop? You calculate the first element. If this element is less than 0.001, you stop there. That will be your partial sum. If not, you move to the second one. Calculate this element, 1 over 1 factorial, which is 1 again. That's fine. Not less than 0.001. You go to the second term, the third term, 1 over 2 factorial, which is 1 over 2, that is 0.5. It is not less than 0.001. You know, you need to move. If you calculate 1 over 3 factorial, 1 over 4 factorial, 1 over 6 factorial. Now, what is 1 over 6 factorial, for example? 1 over 6 factorial is 6 by 5 by 4 by etc. up to 1. That is 1 over 720. And this is not less than 0.001 yet. So we need to continue. Now, if you reach 1 over 7 factorial, this is what I found myself. 1 over 7 factorial is 5040. This number is less than 0.001. Now, this theorem says if you need to have the answer accurate to 3 decimal places, stop here, add the previous elements. If you add the previous elements for the estimation, so if you estimate S by using only S6, adding the first only 6 elements, 1, 2, up to 6, okay? This is the first, let us say, from, this is 1, 2, 3. These are 7 elements, so this is S7. These are 7 elements. The answer will be, your error will be less than or equal to the next element, which is Bn plus 1. So, if you are talking about taking only the first 7 elements for your estimate, your error will be, you are sure that R7 will be less than or equal to Bn plus 1. It means 7 plus 1, that is B8, which is actually 1 over 7 factorial, and that is less than 0.001. So what is your estimation now? The answer, you just add the first 7 elements to get the answer. And that estimate will be, our estimate here will be approximately equal to, okay, it is 0.368. And that will be gained by taking only the addition from 1 up to 1 over 6 factorial. So it is 1 minus 1 plus 1 over 2 factorial plus minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial plus 1 over 6 factorial. That will give you the answer for this specific exercise. I repeat. How to solve the question? I need it to be correct to 3 decimal places, so I need the answer to be less than 0.001. My error to be less than 0.001. So I calculate, I open a few terms, and I calculate each term. If that term is less than 0.001, I take the preceding ones. Why? Because the error here is less than Pn plus 1. So if this is my number, which is less than my error, which is indicated error in the question, I need to take whatever before. So I need to take Sn. Sn in this case will be taking about 1 up to 1 over 6 factorial. That is one application for this theorem. Another application for the theorem, which is very important, says what is the minimum number of terms we need to add In order to find the sum of the given series, accurate to the certain accuracy here, to the indicated accuracy, so we need the error here, our error to be less than 0.001. Meaning, I need my error Rn to be less than, strictly less than 0.0001. Okay? That's what I need. So how to control this error? We know that our error is less than or equal to Bn plus 1. So in order to make sure that our error is less than 0.0001, we need to force this element here to be less than that number. If we are sure now Bn plus 1 is less than 0.001, then our error is also less than Bn plus 1, which is less than 0.001. So what is the thing we need to do? We need to find Bn plus 1. What is Bn plus 1? This is Bn. Bn here is, Bn is 1 over n to the power 4. Okay? Bn plus 1 will be 1 over n plus 1 all to the power 4. Okay? First, we need to observe that this is a convergent series. So I leave it for you to confirm that this is a convergent series. It is a series with decreasing sequence. The limit goes to 0, and that is a simple thing to be shown. Okay, we have Bn plus 1 equal to 1 over n plus 1 to the power 4. We need our error to be less than 0.001. So what you need to force is, if we can make this number 1 over n plus 1, okay, to the power 4 to be less than 0.0001, then we are sure that our error here is, absolute value of our error less than or equal to this, and this is less than 0.001, so our error is less than 0.001. Okay, how to solve this one? This is 1 over 10,000. When you take reciprocal, this will give you n plus 1 to the power 4 is greater than 10 to the power 4. So this implies n plus 1 must be greater than 10. So n must be what? We just add 1 to both sides, minus 1 to both sides, so n will be greater than 9. So you need your elements, number of terms to be greater than 9. So the minimum number is, so we take the minimum number of terms, the minimum number of terms need to be added is equal to 10. So we need to take the first 10 elements to make sure that our error will be, our absolute value of our error is less than 0.001. That is what we call estimation theorem. So we did 2 exercises here about estimation theorem, how to control the number of terms so that we have a certain accuracy, and how to find the partial sums as estimation with a certain accuracy again. Okay, that is what we call alternating series and estimating sums. Alternating series, a specific type of series defined alternately, positive, negative. We have alternating series test that says if the sequence Pn is decreasing going to 0, so it is convergent. And then we have the estimation theorem that says if you are dealing with alternating series that is convergent, then your absolute value of the error will be less than or equal to Pn plus 1, and these are 2 applications for the theorem. That's what we have for alternating series.